So next we have Allan, who will be introduced by Robert Alberon.
All right. Well, I'm Robert Alberon at Electromancer Space Corporation. This summer, I had the privilege of working with an exceptionally bright student, Allan Christensen, who is a rising senior at Stern High School in the San Francisco Bay Area. And this summer, we were using NASA cluster mission data to look at multi-ion uh, distributions during the superstorm of November 2003. And go ahead and take it away, Allan.
We can't hear it, Allan. I think you need to indicate on the share that you're going to share audio as well.
Let me see, how do I do that? Oh, there we go.
Stop the share, and then when you start the share, there'll be a thing that says share audio.
Yeah, there we go.
It's not sharing. Start the share again. Before you actually share, there should be a window that
Yes, I have that checked now, and so let's see.
It was a pleasure to work with you,
There we go.
Dr. Alberon. Dr. Robert Alberon's primary area of research is modeling ionospheric outflows and studying the magnetosphere-ionosphere coupling as it relates to spacecraft plasma interactions. He's also part of the working group of the NASA Science Drive Center for Geospace Storms. This summer, we took a look at geomagnetic storms, which are disturbances in the magnetosphere and ionosphere resulting from variations in the solar wind. These storms are important because of the damage they cause to critical satellite and electrical grid infrastructure. Some of my internship goals were to enhance skills in spacecraft data analysis, Python coding, and data visualization, and to gain experience in space physics topics that seek to understand storm time plasma dynamics that have implications for satellite survivability. With respect to our project goals, we wanted to analyze cluster CIS data with multi-ion distribution functions and differential particle fluxes for H plus, He plus, and O plus species, and to look at relationships between the distributions in differential particle fluxes for H plus, He plus, and O plus ions during a geomagnetic storm. There are three main indices for measuring storm intensity: Kp, DST, and SIM/ASIM-H. We use the SIM-H index because of its 1-minute temporal resolution compared to the 1 to 3 hours of DST and Kp. This provides a higher degree of precision. Geomagnetic storms occur when solar winds at high levels caused by solar flares or coronal mass ejections interact with the magnetosphere, leading to disturbances in the ionosphere. These probability distributions of geomagnetic storm intensities using both SIM-H on the top and ASIM-H on the bottom in nanotesla as measures of storm intensity. To this end, we use data from ESA's cluster mission, consisting of 4 spacecraft, which has already provided invaluable information with complex observations of magnetic reconnection and shock reformation events. Its objective was to look at solar wind interactions in the magnetosphere. The spacecraft are organized in a tetrahedral formation with an elliptical orbit around Earth's poles between 300 to 125,000 kilometers altitude and an inclination angle of 90.7 degrees or so. The mission was launched on the 16th of July and 9th of August, 2000. This was the list of instruments on each of the cluster satellites, and we are focusing on the Cluster Ion Spectrometry Instrument, or CIS instrument, which provides a 3D distribution of ions around the craft every roughly 12 seconds. There were no chronic problems other than C2's CIS instrument failure shortly after launch, which is why we only relied on C1, C3, and C4 for this research. Another note is that the cluster satellites experience eclipses when going through the Earth's shadow during the autumn. While the ESA operated the cluster mission, the data was aggregated to NASA's CDA web database, and the SIM-H data, calculated by the University of Kyoto, was accessed through the OmniWeb portal. With regards to variables, we look at SIMH, which is 1 minute average of the horizontal component of the geomagnetic field, phase space density, which is the number of particles in phase space, which is the configuration space, and the velocity space combined, and differential particle flux, which is the number of particles per centimeter cubed per second per steradian per kilo electron volt. And we also looked at L shell invariant latitude and magnetic local time as spacecraft positions. Of the 7 most intense storms over the roughly 42 years that data has been collected on SIMH, we selected the most intense storm that overlaps with the cluster data, which is the November 2003 storm. For storm analysis, we picked 3 times to plot: a quiet time before the storm, the peak storm time, and storm recovery, demarcated by the extreme changes in SIMH. The storm event we examined took place between November 20th and 22nd, 2003, with a nearly -500 nanotesla SIMH peak value, which puts us over the 99th percentile in storm severity. Given that magnetosphere is deformed as a result of storms, we need to be aware of these limitations when making altitude calculations. Here we can see over the quiet time, the position of the cluster satellites is passing through the southern auroral region, with measurements taken at the dusk region. At peak storm time, we see the positions of the satellites have not moved much from their location at T1, and the Earth's coverage does not impose a significant obstruction to the data. And the cluster quartet had just returned from outside the magnetosphere at storm recovery time, which was potentially influenced by the deformation of the magnetosphere caused by the storm. Throughout this research process, I created Python code that downloads data from NASA's server, creates and exports reduced distributions of several variables to help automate future research. Here we have phase space density and differential particle flux distributions for cluster 1 at the quiet, peak, and storm recovery times. You can see the peaks of the differential particle flux and phase space density are in the same energy ranges, and that O plus is energized during the storm, as we have highest fluxes at T2, then T3, and then T1, which is the quiet time, and the quiet time, which is the lowest for the heavy ions. The H plus and He plus fluxes are also increased in storm time. This slide is similar to the previous, however, it is for cluster 3. It is worth noting that the phase space density is related to the differential particle fluxes with lower mass leading to higher particle flux. O plus has the highest phase space density, but due to its high mass, it has the lowest differential particle flux relative to H plus and He plus. Here we have cluster 4 distributions, and again, the relationship between phase space density and differential particle flux is highly mass dependent, which is significant for the heavy ion O plus and very pronounced in peak storm time, or T2. Key findings in this research were that O plus has the highest fluxes at peak storm time, though H plus and He plus are also increased, the differential particle fluxes are proportional to the phase space density and the square of the particle's mass, and 2 times the energy level of the particle. As for future work, it should serve on the composition of Earth's ionosphere by examining the ion outflows during the remaining storms that occurred during the cluster mission, possibly include simulations from the Center for Geospace Storms MAGE model and the CHAOS model, and to expand the use of multi-point cluster data to disentangle spatial and temporal effects on ion data. Here are the references, and thank you. If you have any questions.
Excellent, Alan. Any questions for Alan?
That was a wonderful analysis of very complicated data.
Thank you.
I'm just so blown away by how great all these projects are. Everyone has done such amazingly high quality work. It's really just, and we're going to get another Robert Sutter student next, I think.
Exactly.
So we'll continue to learn more about geomagnetic storms, probably, or at least particles in space, space plasmas.